Okay, so the title of my presentation is TinyML and efficient deep learning. So we are working on edge AI. So compared with the cloud AI, edge AI has a lot of advantages where there are billions of phones, cars, smart cameras, and edge AI has the advantage of better privacy, lower latency, and lower cost. And there are a lot of data on the cloud collected on the edge these days. So we are working on tiny machine learning techniques that can push machine learning not only to mobile devices, but also to those tiny microcontrollers that has orders of magnitude less amount of computational resource compared with CPU and GPUs. So previously, we proposed this once for all network, which can drastically reduce the amount of computation and train many networks at the same time so that we can specialize it for different platforms. Like we can train 10 to the 19th different subnetworks, and we can select the larger one specialized for the cloud, choose a smaller one specialized for the edge. And those networks are sparsely activated and they share the weight, mimicking the human brain. And also, we deployed this network on diverse range of tasks, detection, segmentation, action recognition, semantic segmentation, etc. So it can provide drastic improvement on diverse AI applications. And once-for-all network can also fit diverse hardware platforms. And to benefit the community, we also open sourced everything. At ofa.mit.edu, we provided 50+ open source models specialized for mobile CPUs, mobile GPUs, and other different mobile platforms. And recently, we are doing even more aggressive to go even smaller, not only to mobile phones, but also to those tiny microcontrollers. So we believe the future belongs to tiny AI, billions of IoT devices. They are much cheaper, like $1 to $2, and much smaller and very affordable. So even low-income people can afford to access AI, to democratize AI. And also they're of super low power to avoid green AI and reduce the carbon emission. But this is super challenging, where from cloud to this tiny microcontroller, the amount of memory is 16,000 times smaller. So this is a huge difference. There's no DRAM, no operating system, no virtual memory. So we have to design everything from scratch, both the inference engine and the neural network model. And conventional model does not scale well. Existing work optimized for model compression, optimized for parameters, but the activation is the real bottleneck. So we propose MCUNet, published in NeurIPS 20 and NeurIPS 21 with the second version, where we greatly pushed the accuracy of ImageNet on those tiny little microcontrollers from a half a megabyte, using only half a megabyte of memory. So here, Olga is the author of the ImageNet. For many years, ImageNet has gone through many updates, but now it is the time where we can deploy ImageNet neural networks on this tiny little microcontroller with only half a megabyte of memory. And still, the accuracy is close to Resident 18, so 71% top line accuracy. And we can enable those real world applications like visual wake-words, face mask detection, person detection, etc. So we believe this will unlock many AIoT applications from videos to point cloud to other complicated AI tasks. And we aim at making AI smaller, faster, greener, and more accessible to everyone through through the TinyML techniques. So more information is available at tinyml.mit.edu. We have many open source projects, and we very look forward to broader collaborations. Thank you.